So in the last lecture of Module 1, we're going to look at further functionalizing the benzene ring. We learned about getting heteroatoms onto the ring through electrophilic aromatic substitution. And we had left off with the nitration reaction, which installed the nitro group, which is electron withdrawing. We then learned conditions to reduce that to the amino group, which is electron donating. And now we're going to take that amine group and do a reaction called a diazotization. And essentially what that is going to allow us to do is transform what was the nitrogen into other atoms, such as fluorine or iodine. And so notice in the prior lectures, we didn't talk about F2 or I2. Those are not typically used to get heteroatoms onto the ring. So we have to have a workaround. And so this is part of, as we learn more reactions, we would say this is a functional group transformation. And so just recalling, we took benzene, we treated that with nitric acid in the presence of sulfuric acid. In step 1 to make the nitro, and then step 2 we were treating with something like, say, tin dichloride and ethanol to do a reduction. And so that took benzene to nitrobenzene and then reduced it to aniline. And so the first step in diazotization is to make a reactive intermediate called a benzene diazonium. And this is actually a salt where the N2 is positively charged and then it's balanced off by an anion, in this case chlorine. So the reagents to do this use sodium nitrite. In the presence of hydrogen chloride or hydrochloric acid, a solvent of water, and we keep the temperature at 0 because this is a pretty reactive intermediate. Essentially what is going to happen is the N2 group gets substituted, and through that process it's eliminated as nitrogen gas. So these are pretty reactive. That N2 wants to leave as nitrogen gas. That gets back to the Gibbs free energy equation, where you're increasing the entropy of the system by generating more products. So what is the role of N2 and HCl? If you look at the aniline, you're starting with 2 hydrogens, and then to make the benzene diazonium, you have N2. So it's supplying that second nitrogen, and it's also getting rid of those 2 hydrogens to form that intermediate. The aryl diazonium salt, again, it has this form. So N2 plus and then X minus, and X is dependent on whatever acid you're using with the sodium nitrite. It's not isolated, which means you're running the reaction in situ. So you're forming it and then you're adding some other reagent to do the substitution. So to make an aryl fluoride, we first make the benzene diazonium salt, and then a reagent that we can use that's a fluorine source is tetrafluoroboric acid. And so essentially what that is, if we expand out, a way to think about it is a proton plus the 4 fluorines bonded to the boron makes the boron negative. And so overall it makes the the fluorine atom's nucleophilic here. So it's essentially going to have F minus in solution. That's going to attack the carbon bearing the nitrogen. It's going to push electrons from the pi bond over to the adjacent carbon. And so we proceed through this intermediate CO minus, and then here we have this minus, and so that's going to re-aromatize by forming the pi bond and then eliminating off nitrogen gas. So again, as you run these, you'll potentially see that nitrogen gas bubble out. And overall, that's going to substitute the NH2 from aniline into fluorine. This process is called ipso, which I believe means same. So it's ipso substitution where the amino group is substituted for the fluorine in this case. So the reagents required to do ipso substitution are generally nucleophilic. And so again, keep in mind when we're talking about these mechanisms, to get the nitrogen on there, we had this nitronium ion, which was positive. We then reduced it down, the nitro group down to the aniline, and then we're making that nitrogen of the aniline electrophilic so it can be displaced. So if we wanted to make an aryl iodide, we would use potassium iodide. So that's your typical inorganic salt. And so now we see that the iodine is nucleophilic. It's going to supply the electrons to do that displacement. And the mechanism is the same as fluorine. Again, I minus attacks here. We form the intermediate, which re-aromatizes, and now we have iodobenzene. Recall from organic 1 the presence of iodide by mass spec. You might see the iodide ion at 127, or you might see a daughter fragment of the parent minus 127 at some lower mass than the parent. So at this point, we've seen we get chlorine and bromine onto the ring using the molecular halogens, but fluorine and iodide, we have to use this kind of multi-step process. Historically, getting oxygen onto a ring is not an easy task, but the diazotization oxygenation sequence is a straightforward way of doing that. Again, we're isolating the aniline, doing the diazotization, and now the reagent that we're going to use is this copper oxide species. And that's ultimately going to substitute the NH2 amino group for OH, and then this molecule is called phenol. And now that we have the oxygen on, we know through resonance that it's an ortho paradirector. So if we were to do a second substitution of that ring, the hydroxyl group is going to direct. Primarily, para will go first, then ortho second, and that's due to steric constraints. We want to get that second substituent as far away from the hydroxyl group as possible. And we know that from IR, we can see the presence of the OH stretch, from 3,500 to 3,000, that broad OH stretch. That's how we know we got it onto the ring. One way to introduce carbon onto the ring is called cyanation, and we know that the cyanide group is equivalent to a carbon-nitrogen triple bond. If we count the number of bonds from carbon to nitrogen, we see it's 3. And so we would say it's at an oxidation state of 3. The carbon, as a review, is sp hybridized. It has 2 sigma plus 2 pi bonds. The reagent we would use for nucleophilic cyanide is copper cyanide. And so it's a nice solid. You can handle it, weigh it. It doesn't pose any particular toxicity concerns. And so it substitutes the amino group for cyanide, and you have a carbon at oxidation state 3 in benzonitrile. And because it has a triple bond, we would see it in region 2 of the IR, and that's from 24 to 2200. And these tend to be very sharp peaks. So they come off the baseline, they go down, and then sort of immediately back up. And so remember, region 2 is your triple bond region. So later on, when we move into the other modules, we'll learn about how we can transform, the cyanide group into, say, a carboxylic acid. This would be called an equivalency. So a functional group equivalency. We're keeping the oxidation state the same, 3 to 3. And it just allows us some flexibility in how we design our sequences. Due to the presence of the triple bond, the cyanide group is a meta-director. So it's going to direct any further substitutions to the meta position. And we know that based on resonance, pulling electron density out of the ring. One further reaction is essentially replacing the amino group, either with hydrogen or deuterium. And so this reagent, hypo, so remember from Gen Chem, the literature, hypo and hyper, or per, that sort of thing. So hypo is the least amount. So hypophosphorus acid. So that has the least amount of oxygens of that phosphorus acid series. Or you could use D3PO2, and that would just install a deuterium. So again, this is if you want to specifically label a position with an isotope, that's the stable isotope of hydrogen. Or the strategy really here is blocking. So you can get that amino group in, you can do some other chemistry, and then remove it. So you're replacing it back with hydrogen. So we call that a traceless directing group. You install it, you do some other stuff, and then you ultimately remove it. And again, that's helpful when you're looking at substitution patterns that really aren't obvious based on the reactivity of the substituents present in the molecule. And so a question here is, given the IR, what reagent was used to quench the aryl diazonium salt? We can see in region 1 this broad hydrogen bond stretch. So we know that that's an OH stretch, has the OH signature. So essentially we're making phenol. So that has to come from the copper oxide. What reagent we use to quench the diazonium salt here? And the signature peak is right around 2200. There's this nice sharp signal coming down, and so that is from a triple bond, and so in this case we've made benzonitrile, and so that has to come from the copper cyanide. So that's going to wrap up the heteroatoms, reactions, getting those onto the benzene ring. What about now getting a carbon atom onto the ring? And so there's two different ways of doing that. They're both called Friedel-Crafts. And the first one we're going to look at is called acylation. And so an acyl group is essentially a carbonyl. So we're going to make a ketone. Specifically, it has to be a phenyl ketone because the phenyl part is coming from the benzene. And the ketone part is coming from our electrophile. And the electrophiles that we're going to focus on are either acid chlorides or anhydrides. And this reagent here is the 3-carbon acid chloride. And what you'll notice, again, if we do this oxidation state, that carbon is at oxidation state 3. We have 1, 2, 3 bonds to the heteroatom. We're using the aluminum trichloride as we saw with the chlorination conditions. And then once this reacts, we end up with this phenyl ketone. And then the oxidation state is now reduced because we only have 2 bonds from that carbon to that oxygen. So overall, the electrophile is reduced from 3 to 2, and we end up with a ketone. So again, the ketone is always going to have this benzene ring, and then whatever is bonded on the other side comes from the electrophile. And so you start with an acid chloride or anhydride in the presence of the Lewis acid, and the reactive intermediate is called the acylium ion. So what is an acylium ion? We'll look at that on the next slide. But wrapping up, because you're forming a ketone, we see in region 3 of the IR the carbonyl stretch. So the Friedel-Crafts acylation invokes the formation of an acylium ion. So remember we said that IUM means that the intermediate is positively charged. What is the nature of this species? So we're starting with the 3-carbon acid chloride. We have an electron deficient Lewis acid. And so look at the aluminum. Again, it doesn't have an octet, so it has an empty p orbital. And one way to think about what happens is kind of something funky we've never seen before. An elimination onto an existing pi bond. So we're going to form a CO triple bond. That's going to displace chloride anion off, which will bond to that aluminum. And so we're going to end up with C, triple bond O. We have our other 2 carbons. Aluminum is now going to have 4 chlorines. So it has to be negative, meaning that the oxygen has to be positive. So A is our correct answer. But how do we rationalize how it bonds to carbon? We can draw a resonance form, where now the positive charge is on the carbon, but keep in mind the positive charge is in an sp2 hybrid orbital, which again is different from what we've normally seen, where a positive charge on carbon is in a p orbital and a carbocation. So this is a special type of carbocation. And this was sort of a problem that I used to give, where you supply the numbers that show the arrows. And so just doing that, drawing the arrows in, we would ultimately write a sequence of digits 8, 3, 5 to 1. And so the purpose of this was that, you're showing 2 arrows. Each has a start and a stop. So 8 is the start, 3 is the stop, 5 is the start, 1 is the stop. It was just a way to help students figure out how to draw the arrows by supplying a sequence of numbers. So the ketone functional group, again, is at oxidation state 2. And we can reduce that down to the alkane at oxidation state 0 using a reaction known as the Clemmensen reduction. That uses a zinc-mercury amalgam, identified this way. An amalgam is a mixture of solids. So typically you would want a homogeneous mixture. We know zinc is a solid, mercury is a liquid. You can react them together to get an amalgam. So we use that amalgam and hydrogen or hydrochloric acid, and it's going to fully reduce that ketone, installing now 2 hydrogens at the benzylic position. And so this strategy of acylation reduction must be used when the chain at the benzylic position is linear. And that will become more evident as we learn the next reaction. But this is also a change of the directing group ability. We saw that ketones are meta-directors because they will pull electron density out of the ring. After we do the reduction, the alkyl group is now an ortho paradirector due to induction. So again, that's another strategy. Just by changing the oxidation state, we can change the directing group ability. So another way of doing that reduction, aside from the Clemmensen, which is a one-step reduction, is forming a species called an acetal. And then reducing that. So we can form an acetal using this reagent here. So This really only works when the reagent has sulfur atoms. And an acetal is a functional group equivalent of an aldehyde or a ketone. Notice the oxidation state stays the same. However, you have an sp2 carbon, but here you have sp3. So they're functionally equivalent at the same oxidation state. And then we can use hydrogen gas with this reagent called Raney nickel. So Raney nickel is just a form of nickel that was developed by a researcher named Raney, essentially where the nickel surface gets really activated, makes it really potent so that the hydrogen can reduce that oxidation state down to 0. So again, this is making a linear aromatic hydrocarbon where that benzylic position coming off at that point is a straight chain. So stated another way, the benzylic position has two hydrogen atoms. So the other Friedel-Crafts reaction is now called alkylation. So remember that acylation, the benzylic carbon is going to be at oxidation state 2. For alkylation, the benzylic carbon is going to be at oxidation state 0. And the electrophile is going to come from an alkyl halide. So that has an oxidation state of 1. When the reaction is run, it's then going to go to the oxidation state of 0. And typically what's going to happen in this reaction is that because we're proceeding through a positively charged carbon intermediate, a carbocation, it's most likely going to rearrange. And we can see that in this first example here where we're taking benzene and making cumene. But look at the structure of the electrophile we start with. We're starting with this 3-carbon chloride, so chloropropane. And so this is a primary alkyl chloride. But then look at the benzylic position. We see that it's branched, meaning that coming off that benzylic carbon, we have a carbon and a carbon. It's no longer 2 hydrogens. So what's going on here? Why wouldn't this just form the linear chain? Why is it now bonding to position 2 of this electrophile? Essentially what happens, because carbocations can rearrange, if we draw this chlorine attacking the aluminum trichloride, we would get a positively charged carbon, so a primary carbocation. Then we balance off the charge. Aluminum is negative. And we recall from organic 1 that if this can rearrange, it will. And so we'll do a 1,2 hydride shift. And that's going to give us a secondary carbocation, which is the electrophile that's going to bond to the benzene ring through electrophilic aromatic substitution. So anytime you see branching and the benzylic position is 0, that is essentially coming from an alkylation. If you see a linear chain coming off the benzene, it has to go through acylation and then a reduction. So in the next couple slides here, we're going to look at reactions that functionalize the benzylic position. And then this is where we really have to start keeping track of the reagents we see and what functional groups they act upon. So in the first reaction, we're going to use this reagent NBS, which stands for N-bromosuccinimide, and that's shown here. And that's a source of bromine that when we treat with a radical initiator, adding heat, it's going to act specifically at the benzylic position. And the reason it does that is because this goes through a radical mechanism where we learned in 255 that benzylic CH groups are the easiest to cleave. Through forming those radicals. So that radical is stabilized, so it specifically acts at the benzylic position. It's not going to act upon any other primary, secondary, or tertiary position. It's going specifically for there. So overall, you've taken a benzylic carbonate oxidation state 0, you formed a heteroatom, and so now it's increased in oxidation state to 1. And then just think about, okay, now you have a bromine, what can you do with that? You can go off into substituting it, SN2, SN1, eliminating it, E2, E1. So you can substitute for other functional groups, or you can eliminate it to make alkenes, and then you can sort of start creating these paths and sequencing reactions together. A second benzylic functionalization is called oxidative cleavage. And so if we're starting with cumene at oxidation state 0 at the benzylic position, we see 3 bonds. We know the fourth has to be hydrogen. So for these conditions to work, the benzylic position has to have at least 1 hydrogen. So one way of cleaving off any other carbon atoms bonded to that position is to use sodium dichromate, sulfuric acid, and water. And that increases the oxidation state to 3, forming benzoic acid. So you've taken something that is, again, an ortho paradirector. You've added an electron withdrawing group, and now it's a metadirector. On the other arrow here, if we were starting with propylbenzene, again, this is the linear chain. We see it has 2 hydrogens. The benzylic carbon is going to remain intact. We cleave off the rest of that chain, and we end up with the same product, benzoic acid. So same thing, propylbenzene is also an ortho-paradirector. We're ending up with that acid group on there. That's now a metadirector. So that allows us to reverse the polarity from electron donating to electron withdrawing to achieve the substitution patterns that we're after. So just as a review, which of the following correctly characterizes the substituent on the aromatic ring? So acetophenone, again, a lot of these compounds just use the common names instead of IUPAC, but acetophenone is this ketone. So there's a carbonyl group that has to be electron withdrawing, so we can eliminate A and D. Ethyl benzoate is an ester. So there's ethyl benzoate that has a carbonyl. That's electron withdrawing, so we can eliminate C. And then we'll see that B is the correct answer, but just let's go through and verify. Ethylbenzene, we have an alkyl group. That's electron donating through induction. So, and then 1-phenylethanol. Would be this. And so that's also an alkyl group at the benzylic position, so that's electron donating. Which of the following correctly assigns the oxidation state at the benzylic carbon? So acetophenone has the ketone, that's oxidation state 2. So we can eliminate A and B. Ethyl benzoate is going to be a higher oxidation state. So we have 1, 2, 3 bonds. That's going to be oxidation state 3, so we can eliminate C, and D is going to be our right answer. Let's go ahead and draw ethyl, benzene. We can see that there's no heteroatoms, so that's oxidation state 0. And then the 1-phenylethanol, we have that benzylic alcohol, so that's oxidation state 1. So if we were to take acetophenone, we said was at oxidation state 2. We did a Clemmensen reduction to make ethylbenzene at oxidation state 0 because the number is decreasing 2 to 0. That has to be a reduction. So our answer here is A. So a reduction is a decrease in oxidation state. An oxidation is an increase in oxidation state. And so you're, again, counting the bonds to the heteroatoms, and then what is the change? Does it increase or decrease? What about toluene to benzoic acid? So this is toluene. This is benzoic acid. So we're going from 0 to 3. That's an increase. So that has to be an oxidation. So C is the correct answer. And the point of these questions is, again, how is that substituent affecting the directing group ability of any further reactions onto the ring? Benzoic acid to benzonitrile. So this is oxidation state 3 to benzonitrile, which is also at oxidation state 3. That's not changing. So 3 stays to 3. So there's no change in oxidation state. And again, we call that just a functional group equivalency. So when you start running reactions on a monosubstituted benzene, so we'll abbreviate this X. So X is whatever substituent. Now you want to do a second electrophilic aromatic substitution. How does that X group affect where the incoming electrophile is going to go. So there's three possibilities, but it's ultimately determined by if it's an ortho, para, or meta director. So for a di-substituted aromatic, if we're going to introduce a group Y, we can introduce it here. Here. Or here. So this would be an ortho isomer. This would be meta. This would be para. So there's three possible isomers for a di-substituted aromatic. So one thing we want to consider now is, because we have this possible distribution of products, how do we differentiate them? And then this gets back to the uniqueness. So let's look at dimethylbenzene, and we'll draw those three isomers. So this is the ortho, this is the meta, and then this is the para. Otherwise, we could say it's a 1-2 relationship, a 1-3, or a 1-4. And the question is specifically asking you which one has the least number of signals in the carbon NMR. And really what we're looking for here is symmetry. And so what I'll do in blue, I'll just draw a mirror plane. So here's a mirror plane of symmetry. Here's a mirror plane of symmetry. Here's a mirror plane of symmetry. But the para also has another plane this way. So that has two planes. The correct answer is going to be para, but let's just go ahead and count for each so that we verify that. So in the ortho, we have 1, 2, 3, 4. So these mirror each other, these mirror each other, these, and then these. So ortho substituted is going to have 4. And again, this is sort of a special case because the dimethyl, those methyl groups are the same. For meta, we have 1, 2, 3, 4. So methyls, this is unique. These are the same. These are the same, and that's unique. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So this will have 5. And then we'll see the para has the least because it has the most symmetry to it. So essentially we have the methyls mirroring each other, these carbons bearing the methyls, and then these mirror each other on this mirror plane, and then these mirror each other on this mirror plane. So if these are the same and then these are the same, they reduce down to 1, 2, 3. So this is going to have 3 unique carbon signals. Keep in mind, if, again, on a di-substituted aromatic, if the substituents are different, these numbers can change. You just have to do it on a case-by-case basis. So here's an example of that. Bromoaniline. And it's asking us for the ortho, the meta, and the para. So here's the ortho isomer. The meta, and the para. So the only one that has symmetry is the para, and so the mirror plane would be here. So let's do that one first. Here's a unique carbon. Now keep in mind that carbon is different from this carbon now because they're bonded to different substituents. So we have 1, these 2 mirror, that's 2, these 2 mirror, that's 3. Then this is its own thing, so this is 1, 2, 3, 4. That's going to have 4 signals. We can eliminate C. Let's circle back now to the ortho. And because there's 2 different substituents, there's no mirror plane here. That's going to make each its own unique carbon. So ortho has to have 6, so that's going to eliminate A. That'll eliminate D. So B will be our correct answer. Let's go through with the meta as well. So 1, 2, 3, 4, 5, and 6. So again, those are things that if you're given data, count the signals and then consider what are the possibilities. See if you can do any eliminations of the responses. So we're given the prompt chloroanisole. So there's a chlorine, but what is anisole? Anisole is methylphenyl ether. So the O-methoxy group, or the methoxy group, is called anisole. And then we want to draw all the isomers to determine what this question is after. So this is the ortho isomer. Here's the meta. And then finally the para. And so the proton NMR says there's 5 unique signals. Let's just go ahead and count the unique sets first, see if we can do an elimination. And then we'll get into this piece of data we're given. So for the ortho, we're going to have 1, 2, 3, 4, 5. So 5, we can't eliminate that. For meta, we have 1, 2, 3, 4, 5. We can't eliminate that. So the answer is going to have to be para. But let's just count those anyway. 1, 2, 3. So this is going to have 3. So for each one now, because we have 2 answers with 5, we want to consider what the multiplicity is going to be for each signal. And we'll write that in blue and see which one jives with the prompt that we're given. We have a methyl group. That's going to be a singlet. This hydrogen has 1 neighbor, so it's going to be a doublet. So we're using that n+1 rule. The next hydrogen has 2 neighbors, so it's going to be a triplet. The next one has 2 neighbors, that's going to be a triplet. The last one only has 1 neighbor, so that's going to be a doublet. So we need a singlet. We have a singlet, a doublet, a triplet, and a triplet. But the prompt says there's 2 singlets, so the answer here, has to be meta. So singlet, this hydrogen has no neighbors, singlet, so that confirms that. But as we walk through, H, that has a neighbor, so that's a doublet. This has 2 neighbors, so that's a triplet. This has 1 neighbor, so that's a doublet. We get singlet, singlet, doublet, doublet, triplet. So our answer for this chloroanisole is going to be the meta. It's going to fit the data for that prompt. So finishing off this last bit of the lecture. So you probably heard my kids playing in the background. I apologize for that. I'm filming this at home. But anyway, once you have a monosubstituted benzene ring and you're forming a disubstituted, how do you predict what the substitution pattern is going to be? So remember that electron donating groups are orthopara, electron withdrawing groups are meta. Let's further stipulate that for an orthopara, the para position is going to go first. So if we have a substituent on there, the second one will go para, just due to steric interactions between forming the ortho isomer. And again, all of this gets back to understanding resonance and induction of the existing substituents. So let's consider this problem here where we're given one molecule that has two aromatic rings. So we'll say the left and the right. And the way we want to consider where would bromine go in a reaction where we have the possibility of two different rings. And the way we want to answer this is we have a benzylic carbon here and here. So which ring will win the race? We classify a ketone as electron withdrawing, and then an alkyl group as electron donating. So this is induction. This one was resonance. So electron donating groups will always react faster than electron withdrawing groups. So that means the right-hand ring has to win. And we know that these are orthopara directors, these are meta. So if this is going to win, we want to say that the para group is going to be substituted first. So D would be the correct answer. So what about now analyzing this molecule, which is overall it's an ester. It has the two issues of a left and a right side benzene rings. We identify the benzylic atoms. We have a ketone. That's electron withdrawing. Then we have this oxygen, which is electron donating. And so this ring will win. It's an orthopara director. B is at a meta position, A is at para, so it's going to substitute here. So for this type of problem where you have two rings, you have to look at the benzylic atoms of each and see, is it electron withdrawing or electron donating? Electron donating is typically going to win, and those are orthopara directors. So in the last couple slides here, we're going to look at making a disubstituted aromatic as a case study where we take, or we want to make this compound called metatoluidine, or essentially you could call this 3-methyl aniline. And again, a lot of this nomenclature uses these common names still. And we want to start with toluene. So the methyl group is already on there, so we don't have to worry about installing that. But now the issue here is this is an orthopara director by induction. So the problem is, just as a substituent, it's going to direct ortho or para, but overall we need the meta-substituted pattern. What that's going to necessitate is we have to block para, because we already said the ortho-para director will go para first. So we need to take advantage of that and block that position. Then we need to further take advantage by using any substituent we introduce to make that go to the ortho. So let's walk through that. Again, we're using the toluene to first direct here to put in a blocking group. That will ultimately direct to the pattern we need to make. We need to block this, install something here, and then remove that blocking group. So the way to do that, we're starting with toluene. We're going to nitrate the para position. So now we have 1-methyl-4-nitrobenzene. The nitro group, however, is a meta-director. So we can't do anything just yet, because if we react now, it's going to install a group there, which we don't want. So we're going to do that switch in polarity where this nitro group is reduced with iron and HCl and water, adjust the pH to get the amino group. So now this is electron donating by resonance, so it's ortho-para. But fortunately for us, the para group is already blocked, so we can't do anything there. So it's essentially in the next reaction going to direct to the ortho positions, which is what we want. So because we ultimately want to end up with a nitrogen, we're going to do a second nitration. And so this is going to make 4-methyl-2-nitroaniline. So 1, 2, 3, 4, that's the nomenclature. Notice that when we get to higher substituted aromatics, we no longer use so ortho, meta, para in the nomenclature. That's only for di-substituted. So fortunately for us, we have now this difference in oxidation state of the nitrogens. This nitro is higher oxidized. We learn this diazotization reaction where we can take the amine, make the benzene diazonium, and now we're going to treat with hypophosphorus acid. And so that is essentially adding hydride, which is going to displace this N2, giving us our hydrogen here. So we've installed the N, reduced it, taken advantage of its directing group ability to install the other nitrogen. We're now going to remove it or deblock it. And then we just need to reduce that to get the correct oxidation state of metatoluidine, which has the amino group. So that's our strategy for making that substitution pattern with the 1-3 relationship. So some strategies to start with. If you're given a compound name, always draw the structure. Once you have the structure, classify the substituents as electron donating or electron withdrawing. Look up the reaction conditions you learned for each of those. What is then the relationship of the substituents? and then just sequence your reactions in the correct order to get that relationship. So some tips on this. Electron donating groups always react faster than benzene, because the benzene pi bonds are acting as the nucleophile, they're more electron rich. Electron withdrawing groups react slower because they're pulling density out of the ring. Friedel-Crafts alkylation installs an electron donating group, orthopara. We see that benzylic oxidation can change that oxidation state at carbon from 0 to 3. And now the acid is an electron withdrawing group, which is a meta-director. Friedel-Crafts acylation installs the electron withdrawing group. You can reduce that benzylic carbon from 2 to 0, and that switches the directing group ability. So acylation is always used to install the linear side chains. Nitration installs an electron withdrawing group, which is a meta-director. You can switch the polarity by reducing it to form the amino group. That's an electron donating group. And the amine then is a surrogate for installing H, OH, CN, or halogens onto the ring. So to practice, here are some substrates that you can draw out and see if you can sequence the reactions together to put all this into practice. So that's going to wrap up the last lecture for Module 1 on conjugation and aromaticity. So don't forget to do your quiz and your exam 1. Those will both be due Thursday at 2:15.